All right, let's see if these are inverses of each other. Remember, you compose one with the other and you see what you get. If you get just the input x, then that's their inverses. So f of g of x equals, so here's f, and I just draw a blank space for the input. Right, f is 1 over x plus 2. So f of g is 1 over g plus 2, and g is 1 over x minus 2. Order of operation. So I got these parentheses just to note where I'm plugging something in, but there's no operation out here, so you can drop them. Negative 2 plus 2 is 0, so you end up with 1 over x, which is x. So 50% done. Now we got to do the other one, g of f of x. So we're thinking, yes, they're inverses, but we got to make sure. So now I write down g is 1 over x minus 2. And then I take this guy and I plug it in, 1 over x plus 2. So this, just like we did here, 1 divided by 1 divided by x is just the x. It means reciprocate that. When it's that simple, 1 over that is just that. So x plus 2 minus 2, and then 2 minus 2 is x. So we verified that those are in fact inverse functions. Okay, good. Well, what if we don't know what the inverse? So what if I ask you to find an inverse? Well, I got a little step-by-step process. I'm going to show you how that works. So I need to find the inverse of 3x plus 1. So here's what I do. Replace f of x with y, just notation. Y equals 3x plus 1. Switch x and y. What's that got to do? That's dealing with our domain and range flip property that we learned about. Now I solve for y. Okay, so I got to solve this guy for y. So I'm going to subtract 1 from both sides. So that gives me, come over here, 3y minus 1. Whoop, that's not right. Try that again. 3y equals x minus 1. And then I got to divide by 3, and I've solved for y. So y equals x minus 1 over 3. And then my step 4 is just my notation for inverses. So the inverse is x minus 1 over 3. That is the inverse of that. If you want to check it, you can compose them together, and like we did before, and you'll get just x. All right, let's try this one. No, that's a typo there. That's x is greater than or equal to 2. That's the domain of that guy. 2. So let's see. Let's try my 4-step process. Y equals square root x minus 2. Flip x and y. X equals square root y minus 2. Solve for y. What's the algebra? I got to square both sides. X squared equals y minus 2. Add 2 to both sides if I'm trying to solve for y. So that's y equals x squared plus 2, and then the notation thing goes like this. F inverse equals x squared plus 2. Okay, let's see. Let's do D next, because that's the easier one. And then C looks pretty complicated, so that should be a fun one. So let's knock out D real quick. D looks easy. Y equals x cubed minus 1. Switch x and y. X cubed equals y minus 1. Y equals x cubed. Switch x and y. Slow down here. Try that again. Switch x and y. X equals y cubed minus 1. Solve for y. Add 1 to both sides to isolate y. X plus 1 equals y cubed. And how am I going to solve for y? I'm going to take the cube root of y cubed, because the cube root of y cubed is y. So I got to cube root both sides. And I get my final answer. F inverse equals cube root of x plus 1. All right, now for this one that looks fairly complicated. Let's see what we can do with this guy. We really got to work on our algebra. Oh, geez. Work on our algebra here. Really rely heavily on our algebra skills. Better give myself some space. All right, so go ahead. Replace x with y. Or first just replace your function notation with x and y notation. So just instead of f of x equals y equals x plus 2, 3x minus 4. Then switch x and y. X equals y plus 2 over 3y minus 4. And I got to solve for y. So how do I do that? So this looks a little complicated because I got two y's. How am I going to get one y? Well, first, do what we'd always do in a problem like this. And that's, if you have a fraction, get rid of your fraction. We learned a long time ago I can get rid of my fraction by multiplying both sides by the denominator. And that kills the fraction, right? So that gives me y plus 2 on the right-hand side. And that's equal to 3y minus 4 times x. Okay, so the goal here, I'm trying to solve for y. So let's get all the y's on one side and all the x's on the other. Or I'm sorry, everything else on the other. So I'm going to have to distribute. So I get 3xy minus 4x equals y plus 2. Get all my y's on one side, everything else on the other. So I'm going to subtract this y over. I'm going to add this 4x over. Okay, so on the right-hand side, I just have 2 plus 4x. On the left-hand side, I have 3xy minus y. So the goal here is to get all the y's on one side because that allows me to solve for y. And the trick I need to do here is factoring. I got two y's. I can't solve for y if I have a y and a y, but if I factor it out, then that'll leave me with just one y term. And then, of course, my last step would be divide both sides by the coefficient of y, which happens to be 3x minus 1. And then I have my inverse function. That was a long one. 2 plus 4x divided by 3x minus 1. Okay, back to the graphical properties. We looked at these. Now, one thing I skipped, which I'm going to talk about now, is that in order to do what we just did here with an example 2, all these examples, if I want to find an inverse function, this has to be 1-to-1. This has to be 1-to-1. This has to be 1-to-1. And what does it mean to be 1-to-1? Well, here's your formal definition. Each y value corresponds to only or exactly one x value. Okay, so here's a function that's 1-to-1 because any y value I choose on here has just one x. This is x squared, but we restricted the domain to 0 to infinity, so it is 1-to-1. Maybe to understand 1-to-1, I'll show you what's not 1-to-1. If I don't have that domain restriction and I have x squared, which is my normal parabola, this is not 1-to-1. It does not have an inverse because this y value right here, let's call it 4. That'd be the point 2,4. So this y value 4 corresponds to an input of 2. But there's another one, right? Because there's another 4 over here. This is negative 2 comma 4. So this 4 also corresponds to negative 2. So this is not 1-to-1. An easy test for 1-to-1-ness is the horizontal line test. If I draw a horizontal line anywhere and it hits in 2 spots, not 1-to-1. If it just hits in 1 spot, it is 1-to-1. Okay, so a couple things going on here. The definition of 1-to-1, the graphical representation. You can do the horizontal line test. If it hits twice, it's not 1-to-1. And that just goes with this definition of for every output, there should just be one input that it corresponds to, not two different ones. And another thing we got going on here is that I can make a function that's not 1-to-1. I can force it to be 1-to-1 by restricting the domain. And that's what I did here. I said, well, okay, I want x squared to be 1-to-1, so I can just limit the domain to 0 to infinity, and it kills the part that's failing my 1-to-1 part, okay, or my 1-to-1 property. Okay, so here's the idea we talked about before. Anytime, so here's x squared. Can you guess the inverse of x squared? Well, what would undo a squaring? It'd be a square rooting, right? Or we could do it this way. Y equals x squared, I skipped a step. Switch x and y, x equals y squared. Take the square root of both sides, square root x equals y. And we've restricted the domain from 0 to infinity, so I don't have to worry about the plus or minus here because there's no negatives. And here's my inverse function, so that should be root x. All right, and you see the properties here, right? Any point that's on x squared, for example, 2, 4. What point has to be on the other one? Well, flip them around. 4, 2. And that's going to give you a reflection around that line, y equals x. Okay, so now we can talk about domain and range. I want to determine the domain and range of f inverse just given f. So the domain of f is, and we know how to do this one. I can't take the square root of a negative, so I'd have to do this guy. Which means, and I solve that for x, the domain of f is anything greater than or equal to 2. So that's equivalent to the range. I don't even have to look at the inverse function. That is the range of f inverse. They're the same. Right here. And in interval notation, that would be 2 to infinity. That's the domain of f, but also the range of f inverse. All right, so what's the range of f? Range of f. Well, if you know your root function, we don't have to do a lot of work here. You can kind of imagine the graph. It's all positive values, right? So the range of f is 0 to infinity. And that has to be equal to the domain of f inverse. All right, so think about it. We just looked. We didn't even look at, we don't even know what we could find f inverse, but we didn't even bother. We said, okay, I know what the range of f inverse is if I look at the domain of f. I know what the domain of f inverse is if I just look at the range of f. Okay, one more. So we already have a restriction here because we know that if I don't have this restriction, it's not 1 to 1. Right? X squared minus 4. If I didn't have this restriction, x squared minus 4 looks like this. Not 1 to 1 doesn't have an inverse. But if I restrict the inputs to positive values or non-negative values, then I'm looking at this guy, and this is 1 to 1. It would pass that horizontal line test. Okay? So the domain of f is given. So I don't really have to do anything there because that's the restriction for f. So that's the range of f inverse. Done. And in interval notation, that's 0 to infinity. So I got the range of f inverse, halfway done. Now I need the domain of f inverse. So I look at the range of f. Range of f. And my graph really helps with this. I just do a quick sketch and I see the range of f starts at -4 and goes to infinity. Just based on my quick sketch, based on my knowledge of quadratics. So the range of f then is the domain of f inverse.